Okay, we're going to pick up where we left off. We have another polynomial function, or sorry, a rational function, polynomial in the numerator, polynomial in the denominator. This one's already factored for us. So we're going to take a look at what happens here. Now, you might have, from what we talked about yesterday, you might sort of be in this idea that like once you can factor and cancel, you automatically get a limit. This is an example where that is not necessarily true. It's not true. So you can see, because this is already factored, that when we go to do the limit as x approaches -3, I'll start here at the bottom with the overall limit. When we do limit as x goes to -3, we would have the limit as x goes to -3 of that fraction. And we've got x plus 3 squared, x minus 1 squared, and x minus 2. Boom, boom. And when you went to cancel, the thing that would happen was you could cancel the x plus 3 with one of the two x plus 3s that you have in the denominator. X plus 3 squared is as good as having that factor twice. So when you cancel one of them out, you only have one left over. Really common to just, cross out that 2 like that. As you can see here, even after you've factored and canceled, you're in a situation where you get 0 in the denominator, because plugging -3 into x plus 3 gives you 0, and you get a non-zero in the numerator. That tells us that we're going to have an asymptote. Non-zero over 0 means asymptote. That's the big thing in this lesson. So that means we need to do a sign chart. We're not going to put a number here. We're going to do a sign chart, and only if the signs match will we write infinity there. Otherwise, we're going to write does not exist. So I'll go ahead and make my sign chart. The numbers that I need are -3, 1, and 2. As silly as it sounds, make sure your numbers are in order from least to greatest. This is representing a number line. And then what we're going to do is, just like we did yesterday, we'll start on the numerator. The numerator is x minus 1, but squared. So we'll talk about this in a minute. But what that means is, just from a making the sign chart perspective, any number less than 1 is going to make x minus 1 negative. Any number bigger than 1 is going to make x minus 1 positive. But it's not enough to just write one of those signs in your sign chart, because this is x minus 1 but squared. So there are two x minus 1s in that numerator. They're just pushed together because they're the same thing with the exponent. So we actually, if we're doing the sign chart to show exactly what's happening, we need to put 2 of each of those signs. Now, here's the thing about that, though. Anytime you have something being squared anywhere and you're making a sign chart, you're always repeating 2 of the same signs, and that doesn't do anything to the overall sign of your function. So the 2 minuses together will cancel out to give a plus, and the 2 positives together are already going to give a positive. So it does turn out that, you could either draw this in just to make sure you're doing the right thing, but if you're really thinking about this, anytime you have an even exponent, you could just leave that completely out of the sign chart. Squaring something keeps it positive, so it has no effect on the sign, doesn't need to be in the sign chart. So I'll leave those there, but just knowing that they did not need to be there. Next, we'll do x plus 3. That's going to be negative before -3 and positive after. And then I'll finish up with x minus 2. Grab myself a different color here. There we go. And that is going to be negative before 2 and positive after it. So negative, 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 positive. I can now look at my overall signs. And again, I'm ignoring the top. I could think about it. I could think about this first section as having 4 minuses, but ignoring those top, I just have 2 minuses. Either way, I realize that my values of my function are positive to the left of -3. They are then negative to the left of -3, or sorry, to the right of -3. Around 1, they don't change. And then after 2, they are positive. So if you put this function in Desmos, you would see that the graph had whatever it looks like. Now there's going to be some asymptotes there. The graph's going to have asymptotes at 3, but the function is going to be positive before -3 and go up. It's going to come from the negatives before -3. It's actually going to be equal to 0 when you plug 1 into it because of the x minus 1 term. but it's not actually going to cross over. And it'll stay for a negative asymptote at 2. And then that asymptote will come in positive. So that's just a very, very rough sketch, just thinking about asymptotes, really just thinking about asymptotes. I was just over talking myself when I was talking about hitting 0 there. But that tells us that the limit as x approaches 3 from the right is negative infinity. Oops. I feel like I need to reset a setting on this so that doesn't happen. All right. Coming in from the right is negative infinity. Coming in from the left is infinity. I can never seem to be consistent with where I put my pluses and my minuses, which one I do first. But yeah, so negative infinity and positive infinity. For whatever reason, on the right-hand side, or on the next line, I have them like totally backwards. So I have 2 right on the bottom, and 2 right is positive infinity. 2 left is negative infinity, and the overall one then does not exist. And that is also what I should be writing over here. None of those limits exist, right? Remember that. Writing does not exist is not writing something different than infinity. Infinity just gives us more information. Cool. And then last but not least, the limit as x approaches 1 is just 1 being plugged into this function because there were no problems with 1 in the denominator. I guess the reason I have this one here is because the issue is with we looking at our numbers to make our sign charts, these are numbers that make things 0. The 3 and the negative 3 and the 2 are so important because those were what made the denominator 0. If you just have a number that makes the numerator 0, then your whole function evaluates to 0. When I plug 1 into this function, I get 0 right here. I'm then multiplying it by stuff and then dividing it by stuff that isn't 0. So my answer overall is 0. Okay. I decided after thinking about it, actually when I printed this out as well, I just didn't have time to edit it, that I was going to leave this part out for now. We're going to talk about this later on in a spot where it makes a little bit more sense and isn't just something piled on. So crossing that out allows us to then cross some homework problems out, which I know for a fact I'm going to go with. That's going to cross out 9 and 10. 9 and 10, and probably 8. We'll keep everything to rational functions. The only one that really will be a challenge problem that might somewhere be in that, but really isn't. No, number 7. Number 7 will work too. Yeah. Okay. And yeah. All right. So let's take a look at our last example. Yesterday, when I finished off class and kind of said where we were going to finish this up with, I said that the question that we're going to do next is really the same question. It's just asked differently. So you're going to do all of the same stuff. There's one little extra piece. You've got to figure out the limit as x is approaching something. But that's pretty easy to find. It's just the same numbers you're using to make your sign chart. So here we go. We've got letter A. Again, a polynomial function, 1 over x squared, 1 minus x squared over x squared minus 6x plus 5. We are going to factor that. This one does have a little bit of something extra in it. This is going to be 1 minus x times 1 plus x. So we kind of took our usual pattern where the x comes first and swapped it around. So it's 1 minus x squared. And our bottom should be a pretty easy factor. It is x minus 5x minus 1. I had 3 and 2 in my head when I was doing that. I was thinking, but nothing's factoring and canceling. We're good. Okay. So again, we've got a situation here where it doesn't necessarily look like anything matches perfectly. Remember how this works. This is important. Things either need to match exactly or have completely opposite signs. So I've got an x minus 1 and I've got a 1 minus x. I can do something with those. I have to factor a negative 1 out of one of them. Okay, so it works when all of the signs are different. On the other hand, if you have like 1 minus x and negative 1 minus x, there is nothing you can do with those two. So it's got to be all opposite signs because that's what's allowing you to factor that negative 1 out. So I'll do one more limit, or I'm sorry, I'm not doing a limit. yet. So I'll do -1. I'm factoring that out of just the first term. I'm going to leave the second term alone. That's how the algebra works. So -1, this is going to be a -1 plus x or an x minus 1. And leave this as a 1 plus x. And here we have x minus 5, x minus 1. And now we see we have a factor and cancel. I'm not canceling anything here because I'm not working in a limit. I'm saying that this function at the beginning is the same as this function at the end. And as soon as I cancel something, I might be adding more numbers into the domain than actually are there. So we'll deal with that in the limits. Our two possibilities for asymptotes are 1 and 5, but it should be pretty obvious that the limit as x goes to 1 is going to exist because we'll be able to cancel these guys out. So there's not going to be a horizontal or just a vertical asymptote at x equals 1 because the limit as x approaches 1 of f of x is, I'm going to go ahead and, let's see, the limit as x goes to 1, I'll do it this way. I'm going to write everything except for those x minus 1 terms. So -1 times 1 plus x over x minus 5. So what I've done there is I've taken and I've canceled these guys, and I've written everything else. And then we will get, looks like we have -1 times 2 in the numerator and -4 in the denominator. -1, 2, yep. That's 1/2. So we do not have a vertical asymptote at x equals 1. But at x equals 5, we will have that vertical asymptote. And that's because the limit of our numerator, and now I'm going to show you how to write this. The limit as our numerator goes to 5, and then 1 plus x, I'll write the whole thing out. Oop. That's going to be 4 times 5 is 20, is -20. And the limit as x goes to 5 of the denominator, x minus 5, x minus 1, is equal to 0. That means I'm going to do a sign chart. That sign chart is going to have a 1 and a 5 on it. Although I really don't need the 1. The reason I don't need the 1 is because it's going to have the same sign in both the numerator and the denominator. So we actually have to do 3 pieces, and this is why I have this example. That -1 is one of the pieces. -1 is always there, so I need a negative sign in all 3 parts of my sign chart. X minus 1 shows up in the numerator and in the denominator. Optional to put it there. I'll show it. Negative before 1, positive after 1 is doing nothing towards the overall sign of this sign chart. Finish off with x minus 5. Need like one more pen here. Negative before 5, positive after it. I think I'm good there. So my overall signs are plus, plus, minus. And here's the deal with this. This problem is saying to both identify the vertical asymptotes. I've said it already, but now we'll kind of, we'll actually write it out as our answer. And then the next part of it is going to be the justification. Anytime you see that you need to justify something in AP Calculus, especially thinking ahead to May on the test, there is some specific thing that they're looking for that is a correct answer. This is not open-ended. This is not, I can say it this way, you can say it another way. There is a vertical asymptote at x equals 5. And that's because, and here's what you need to show. You need to give one limit as x approaches 5 and show that it's infinity. In this situation, there is a small choice here because you can either pick 5 left or 5 right. If these two signs matched, you could pick 5 overall. But since they're different, I got to pick one or the other. I'm going to pick 5 left because I need to pick something. So, and that is because the limit as x approaches 5 from the left of f of x is positive infinity. It's positive infinity because all of the values that are a little bit less than 5 are positive according to our sign chart. So when you look at a problem like this, what you end up having to do is kind of two things. You need to factor it, obviously, but then you kind of have to look at your denominator and decide whether those values are good or not. You kind of, I shouldn't say you do two things. You go in two directions. If you get completely canceled out of the denominator like x minus 1 does because of the, in this case, the factoring out, but if you get completely canceled out of the denominator, you are not a vertical asymptote. If after cancellation you're still there, then you are a vertical asymptote. Make your sign chart, pick one of the side limits. That's your justification for being a vertical asymptote. Vertical asymptotes happen when you get a limit that equals infinity. All right, with that being said, we're gonna hold off on letter B. I wanna do that in person with you guys. This is one last technique that we have to do, obviously because of the tangent. These are things that we can figure out based on what we know about sine. I mean, we are still going to have a fraction here because we're going to do sine over cosine. But this argument of 3x is going to give us a little bit of a, not a hassle, but it's going to add a step to the problem. So it's something that's probably brand new. And we'll talk about that in person.